Thank you for being here. I will talk about air quality assessment in PM Inter, a new integral sustainable approach. Let me briefly say something about the European Union funded project PM Inter. It's an air quality driven integral assessment approach. The initial motivation for this project were the frequent breaches of air quality standards in this area. And the aim of this project is to support a sustainable improvement of air quality in the project region, which is shown here on this map in green. This area here, and thus to reduce health risks for residents. And so one of the major aims of this project was to develop effective air quality management plans. Here in this area, it's southern of the Alpine Bow, very sheltered from strong winds. There are two main cities. There is Klagenfurt here and Maribor there. They have approximately 90,000 inhabitants each, and there is almost no industry. And on the right-hand side, you see the days which exceed the daily mean of 50 micrograms per cubic meter for PM10, the number of days. And here on the lower line is the Austrian limit, and the upper line is the EU limit. And you see here quite some frequent breaches, and especially here at that station, there are 73 days exceeding these 50 micrograms. That's in a town with 9,000 inhabitants. The critical air pollutants there are nitrogen dioxide, which is toxic, particulate matter, commonly termed as PM, which is toxic and carcinogenic. PM10 is the mass below 10 micrometers in diameter, and it's inhalable. It's a complex mixture of solid and fluids, and there are primary sources for particulate matter, which is mainly traffic, residential heating from wood, coal, and construction. And there is a secondary formation path. This is secondary formed particulate matter. Precursor gases like NO2 from traffic or SO2 from industry react with the OH radical to form strong acids. These strong acids, here nitric acid for instance, can react with ammonia from agriculture, and those two components can then condense to a liquid phase or a solid phase on existing particles, the primary sources. And this is a very important process since it links different sources and it undergoes transport over large distances. And also approximately 30 to 50% of the wintertime PM in Middle Europe can be attributed to the secondary particles. I would briefly introduce you to the main concepts of monitoring and simulations. On the left-hand side, there are the emissions as a mass rate per time, and on the other hand, what we breathe in is a concentration, typically measured as micrograms per cubic meter. But there is no direct way from concentration, from emissions to concentrations. It always needs mixing and transport and chemistry to arrive at the concentration levels, and over time this is actually the exposure. Modeling allows us, in contrast to measurements where we have only one position in space, to obtain a spatial figure by programming, let's say, the physics. We used even two models in this PM-Inter model, modeling approach. On the left-hand side, you see a model type. It's a chemistry transport model, where we start with mainland Europe to simulate the air chemistry, and then we have here a red box which covers the alpine bow and the foothills, and then we have some smaller boxes in there. We refine the computational grid more and more, and we end up there at the smallest domain, here shown again, with 1 kilometer by 1 kilometer horizontal resolution. And that's important that we can simulate these very concentrated pollution burden in alpine basins and valleys. Otherwise, this pollution gets smeared or blurred over the hilltops, and where there is actually poor air. And you can see we go even one step further. Here, these three black areas, 12 by 8 kilometers in size. There we defined 3 microscale core areas where we simulated the particulate burden on even 10 meter by 10 meter. And we combined those two models because we also wanted to capture transport processes and these processes close to strong sources like roads. This shows you already results for PM10, for the large domain, which covers the Alps and foothills at 5 kilometer resolution, a typical resolution where the finest emission inventories for Europe are available. And you see not much gradient. Actually here, this is Graz, where I come from, which is sometimes called the European capital of fine dust. Here actually this value is underestimated by a factor of 3. And up there is Munich, Vienna we can't see, and yeah. But if we go to finer resolutions, we approach the target area and we see far more detail already. And this is enlarged, and now we have far higher concentration levels with that approach at 1 kilometer by 1 kilometer, but we are still not good enough. Here in Leibniz we are 30 micrograms away, in Klagenfurt about 10 micrograms, and in Maribor also about 10 micrograms. And combining those two model systems gives that picture for this microscale core area. Here you can already see quite some detail, the strong concentration gradients close to major roads, but also here these maxima which are related to wood burning and coal burning here in these areas. Also here we have villages with significant PM burden. An important part of this modeling work was validation. Here you see an example for the simulated windroses, which is in blue, and the observed one. It fits quite well. And what's very important for this area, that we can capture the low wind speeds which are prevailing at the time of the year in January 2010. Well, because they contribute a lot, or these conditions contribute a lot to the actual monitored and also simulated burden. Here on the left chart, you see the scatter plot when we compare observed values against simulated one for the Wolf-Chem model with 1 kilometer resolution, and the R square is pretty low, it's 0.16. On the right hand side, when we combine those two models, we have a R square of 0.95 and a far better agreement. Also, we compared our simulated results to filter measurements carried out by Urhner for 6 monitoring sites. These are the 6 monitoring sites, and on the left column of each monitoring site you see the simulated results, and in the middle column the measurements from the filter analysis, which was carried out in February 2011. And here on the on the right columns you see the measured value for January 2010. And what you see here is that there is a good agreement between the simulated and measured values, and for all stations actually. And also what you can see is that the components, the main components here in brown, this is the PM from related to domestic heating, mainly wood smoke, and also here the upper part of the column, secondary inorganics. They are captured quite well for these stations. These are the main components. And there is another one, the black one, it's traffic exhaust. These are soot particles. The tendency is captured quite well. There is a slight underestimation for some locations within the simulations. Here, this shows you the spatial distribution of traffic exhaust and the simulated concentration level, and on the right-hand side, residential heating. And you can see the soot particles originating from traffic are on a quite smaller level, above 2 micrograms. The concentrations are illustrated here, and only here at tunnel portals or main motorways there are elevated levels. But here we have very high levels, up to 20 micrograms as a January mean. Down there you see the distribution of different residential heating facilities. Here the major part in this orange is oil, and this quarter here belongs to wood. Here the emissions originating from different fuels are plotted, and you can see PM10, 90% of the emissions relate to this quarter of wood burning. However, when you look at the CO2 in tons per annum, there is only a small part which relates to wood burning, and the majority is again can be attributed to fossil fuels, which are here from blue until the purple. We evaluated quite some scenarios. Usually scenarios are air quality driven and pollutant specific. However, secondary inorganics links different sources like NO and NO2 from traffic, and power and heat generation, ammonia from agriculture, and SO2 from industry and power and heat. It's important to know greenhouse gas emissions have the same major sources. Firewood may cause high PM, but it's a renewable. There's a contradiction between greenhouse gas goals and air quality targets. So I will show now some results from scenarios. Here we replaced individual heating facilities by biomass district heating in Klagenfurt. Here at that site an additional 95 megawatt biomass district heating plant is planned actually, and it shall produce 175 gigawatt hours district heating. And in this area here we replace individual burners and stoves for light fuel, oil and solid fuels. And this is actually the result, the PM10 reduction, which relates to this scenario. And this is mainly due struggle with this technique. Yeah. So, shall I move to the conclusions?
Yes.
Yeah. This is my summary. Unfortunately, I did run out of time. So, PM is dominated by secondary inorganic aerosol and wood smoke PM. High PM levels are attributable to sheltered locations and the meteorological conditions there. So that means the Southern Alp locations, the valleys, and the street canyons. The chosen modeling approach enabled a fractionated representation of regional and curbside PM pollution and resolution matters. And in terms of the efficiencies of concerning the scenarios, I have listed the three most efficient ones. So one is the biomass district heating, where I have a high efficiency in reducing greenhouse gases, but also I can reduce area-wide on an urban level 2 to -3 micrograms per cubic meter. And that's a lot. Also, I can avoid benzopyrene emissions. And very efficient is also reducing on a regional level ammonia from agriculture. And depends on how this measure is achieved. I can have also a positive impact, for instance by veggie days, on greenhouse gases. Also quite effective, especially in terms of NO2 reduction and CO2 reduction, is increased public transport, park and ride, and access limitations in the inner city and an environmental zone in Maribor. Okay. Thank you for your attention, and this is, by the way, Klagenfurt.
I'll try to be quick to leave time for more discussion at the end. And what I'm basically going to present now, it's a little bit of a wider picture of our group's research activities on urban design and air quality. So basically, the first question is to why, and the first answer is because urban planning decisions affect environmental outcomes for years to come. The roads that we're still using here were laid out several years ago, and that does put some constraints on what you can do and what you can achieve. But also, and this is a figure from a paper from 2011 that actually shows this long-term impact of the design of the cities. Depending on the shape of the urban areas and the accessibility to public transport and the feasibility of public transport, it does determine, to a degree, the air quality outcomes that can be achieved in these areas. Now, as I said, I'm going to show you here a little bit of our research program, which is funded through our core funds in NIWA, which means just that we have a long-term platform to do this kind of research and allow us to focus on questions that don't necessarily have a one-year answer. Like, how does the pollution, as Ulrich mentioned, that's emitted in one place ends up as a concentration measured somewhere else and determines the exposure of people, and why and how is that exposure varying between individuals. Now, in urban areas, there it is, topic. Urban areas are very diverse, and depending on where you are is what you're experiencing, but also depending on who you are is what you're experiencing. And in terms of air quality and exposure to air pollutants, it's documented differences. This is a sample plot of a couple of runs that we made, where we put some air quality sensors on people, not quite parenting a child, but the researcher simulated being a parent and simulated being a child. And the black curve is the exposure experienced by the adult, whereas the red one is experienced by the child. And you see that they're different first, and they peak at different times, they go to different places, and as I said, in terms of air quality, they experience the city differently. Now that puts a challenge to us as air quality researchers, in that we need high spatial and temporal resolution measurements to actually understand that difference in exposure and characterize the different microenvironments in a city. As Ulrich mentioned, the resolution of your modeling approach and measurements here, it's key to actually observe what you want to observe in terms of assessing the problem, but also evaluating whether what you're doing is actually making any difference at all. And this is from a project that we named Roadside. We weren't being very original then. Where we measured a number of things next to a highway, and our goal was to understand and characterize the impact of these significantly trafficked roads on the exposure of people living right next to it. The application of these results actually end up in this thing. One is from an NZTA, a New Zealand Transport Agency website, where a model that stems from that kind of work is being used as a roadside assessment or a screening tool, whether the NZTA will pursue or not expanding a road or building a new road. But it can also be used, and it has been used, to develop or to assist in the development of land use rules. That's the map on the right. Yeah, that's the right one. That shows early childhood education centers and elderly care centers located near major roads. And that's the link that we were trying to bridge, the impact of these major roads on the sensitive receptors. Now, unfortunately, that approach didn't quite work on the heavily built areas, the CBD, I mean, more of the high-rise, very dense built areas. It just didn't work. We didn't plan that campaign to do that. So we planned a different campaign, and this one we're being more adventurous with the names. One's called PNAD, that stands for pollution, people exposure to pollution and noise, something like that. And Spartans, that's cooler. And it's a much longer name that I just can't remember now, which is the goal of the acronyms, that you remember that one. But this was basically both projects aimed at measuring with a distributed network of air pollution sensors with very dense network in the Auckland CBD, both nitrogen dioxide and particulate matter. This is from nitrogen dioxide and this is from particulate matter, and it's a picture of the sensors that we deployed, and correlate those measurements with other parameters like land use, like traffic flows, like building height, like footpath clearance, with the main goal of actually transforming and converting this data into information that can be actionable. So taking transport data, traffic, public transport and bus movement data, traditional air quality monitoring data, that in the case of the Auckland CBD, there's actually an Auckland Council air quality monitor down there, meteorology, etc., to convert this and understand why the levels are those observed and what can we do about it. And this is where the TOTUS that Philippa mentioned comes in. And this acronym, again with acronyms, well, I came up with that several years ago, and I still get flack about it. It's a liberal choice of letters, but I think it works. It started as a towards sustainable urban forms, as a project focusing on quantifying the impact of the urban form on air quality outcomes. And the word totus in Latin means all-encompassing, primarily because in urban areas we have all sorts of layers and parameters and activities that control the outcomes that we want to achieve. So we set out in a very ambitious way to develop a modeling and database framework that's able to incorporate and integrate different information layers and model systems to enable comparisons of the kind of what would be the exposure of someone living here and wanting to work as a accountant, just to mention something, on two given scenarios. What if we put a shopping center here with lots of work areas and therefore an accounting firm here, or we put it somewhere else? So it's our aim to move from characterizing and evaluating the personal exposure of the population, moving through an air pollution field in an urban area. Now we've used that, and it's actually available for anybody to have a look at. But the kinds of questions we've used it so far, if you focus on this upper right corner there, that's school travel patterns. That's a bunch of schools in Auckland where we have data from where people live and what do they use to go to school. And we use the total system to generate estimates of how much traffic the kids are exposed to when going to school. And the color of those bubbles represent, the red colors represent a lot of traffic in going from home to school, and the green colors represent very little traffic. The size of the bubbles represent the average trip that the students take to go from home to school. So this enables us to identify some schools that have a very large have a very small footprint and their students are exposed to very little traffic. that in itself is just data, but that's data and information that wasn't there before because we didn't have that platform to enable that, thank you, to enable that comparison and that analysis. And now if we move to the bottom panel here, this is a more contingent or interesting exercise. The map here is the impact of the earthquake in Christchurch on the traffic flow. Well, that's not quite true. It's the impact of the earthquake on the traffic flow as observed or as estimated in the long-term nitrogen dioxide concentration field. So areas here in the CBD or downtown Christchurch where no traffic, no car were traveling after the earthquake, so improvement on a reduction on the NO2 concentrations, where some areas in the outskirts here saw an increase. And in terms of population, that can be summarized as a few people got a better air quality after the earthquake, and a lot of people got it worse. And that kind of assessment, that kind of information, we believe is useful for urban planners and for policymakers, so that the policies are informed by science. Now this figure here shows our demo website that everybody's welcome. I'm going to give you the address in a minute. To have a try on. It's on purpose. It's very light on documentation because we are seeking feedback from anyone and everyone on what kind of information might be useful to have there, what information, what mechanics, how can you use a system like that, and any feedback is very much welcome. So what now? As Philippa mentioned, we are working hard in developing the total system within the Resilient Urban Futures program, and our main focus at the moment is on usability and relevance. So the goal is to, and that's why the questions I asked before, what would the system work best or better for you, and what kind of information would be more relevant. So what kind of other layers we could add to that system now that anybody here may have an interest around, like planning scenarios, demographic changes, or energy policy. And on that energy policy, because of our flexibility, and let me go back here, we do have in the total system an energy consumption module that enables us to estimate the energy consumption for different urban forms and urban land uses. So as I promised, here is the website that everybody's welcome to click on, or just write down like that. And I think I did very good on time. Thank you very much.